I'm going to prove the expected value and variance of a binomial for those who are interested in seeing the proof. So I told you that the expected value of x, if x follows a binomial, with n and p being the parameters, is n times p. Well, again, intuitively, I think this makes sense to everybody, but we can also prove it. And there's a little trick to proving that this is the case. So we're going to prove it by starting to look at only a single trial. Remember, all the trials in a binomial are equivalent, so we can just look at one case and then extend it to all cases. So when we have one trial, x can either come out to be a value of 1, a success, or a value of 0, that's a failure. There's a probability p of success and a probability 1 minus p of failure. So if I ask, what's the expected value when you just have one trial, it's just going to be, how do we calculate expected value? We multiply x times its probability, so 1 times p plus x times its probability, so 0 times 1 minus p, which of course just simplifies down to p. So that's the expected value for one trial. Well, how do we then go from there to the expected value of n trials? Well, we can recognize that the total binomial count is just going to be equal to, if I take each trial, it's going to end with a 0 or a 1, and I add up all those zeros and ones, that's going to give me the total binomial count. So another way we can write that is we can say that the total is just equal to the sum of all the individual trials from I equals 1 to n. So if I wanted to ask, what's the expected value of that sum? Well, it turns out that the expected value of a sum is just the sum of expected values. Well, since we know that every single trial has the same expected value, which is equal to p, then we're just going to add p from 1 to n. So we end up with n times p. So that's the proof of the expected value. The proof for the variance is just slightly more tricky, but not really much different than the proof for expected value. So what's the variance of x? I told you the variance of x, if x is a binomial, is n times p times 1 minus p. Again, we're going to prove this by starting with just a single trial. What's the variance for one trial? So again, for one trial, x can either be 1 with probability p or 0 with probability 1 minus p. Well, how do we calculate variance just for that one trial? What's a variance? Well, we have to know that in this case, the mean, the expected value is p, because we're going to be subtracting from the mean. So let's say we get a value of x equals 1. So we would do 1 minus the mean, which is p, square it. That's the squared deviation of the mean if x ends up as 1. How often does that occur? It occurs at a frequency of p. So we have to weight by the probability with which it occurs, which is p. The other alternative is that you end up with an x of 0, subtract p. That's the mean again, square it, multiply that times 1 minus p. The rest now is just a bunch of algebra, but I'll do out the algebra. It's kind of fun. So p times, now we've got a 1 minus p squared. We're going to have to FOIL that out. I'm going to move the single p to the front, and then I'm going to FOIL this out. 1 minus 2p plus p squared. If I apply FOIL here, I expand, binomial expansion of 1 minus p squared. Then I'm going to say, well, okay, 0 minus p squared is just p squared, so this becomes p squared times 1 minus p. Now let me just distribute the p here, so that becomes p minus 2p squared plus p cubed plus, and let me distribute the p squared minus p cubed. Now the p cubes look terrible and awful, but the nice thing is you'll notice that the p cubed fortunately cancel out, and one of the p squareds cancels out. So we've got a p squared minus 2p squared, so that just becomes a single minus p squared. So this simplifies down to p minus p squared. Another way to write that is p times 1 minus p. That's the variance for a single trial. Well, it turns out that the variance for the sum, remember if we add up all the x's, that gives us the total binomial count. The variance of a sum, if we have independent trials, is equal to the sum of the variances. And again, we talked about this if in an earlier module. So the variance of the sum is the sum of the variances for each individual trial. That is true if we have independent trials, which we do in a binomial. Well, each variance. Each individual trial has a variance of p times 1 minus p, and we're going to add up over n of them, so that just gives us n times p times 1 minus p. So that's the proof of the expected value and variance of a binomial.